Did you know that millions of dollars and massive federal contracts are lost every single year? And it's not because a product actually lacks security, but simply because of a fundamental misunderstanding of cryptographic engineering. Welcome to today's Explainer, where we are tearing down the assumptions around FIPS 140-3 compliance. We're going to look strictly at the engineering realities, the compliance roadblocks, and exactly what it takes to survive a modern validation audit.
So here is our roadmap for today. We'll cover what FIPS 140-3 actually is, the 4 security levels, some dangerous engineering assumptions, common pitfalls, the implementation roadmap, and finally, how to prepare for post-quantum cryptography.
All right, let's kick things off with Section 1. What is FIPS 140-3? A structured engineering program. Look, we have to shatter the illusion right now that FIPS 140-3 is just some simple configuration toggle you can flip on a server. It's really not. It's a highly structured engineering, compliance, and validation program administered jointly by NIST in the US and the CCS down in Canada. Just look at the transition from FIPS 140-2. The old standard was a standalone US document with statically defined algorithms. FIPS 140-3 completely changes the game by harmonizing with international ISO and IEC standards. But, and this is key, NIST still pulls the strings for North America by dynamically governing the rules through their special publication 800-40 series.
Now, what's really fascinating here is how these special publications actively modify that international ISO base to mandate strict North American regulations. For example, SP 800-140CR2 steps in and restricts block ciphers strictly to AES. Another document, 140DR2, mandates exactly how asymmetric and symmetric keys must be generated. It's this exact intersection of global testing methods and strict regional rules that truly defines FIPS 140-3. Moving right along to Section 2, the 4 levels of security. Qualitative protection metrics. You see, FIPS 143 isn't a one-size-fits-all standard. It scales across 4 distinct security levels. The underlying mathematical cryptography, the actual AES or SHA-256 algorithms, well, that doesn't change between these tiers. But notice the extreme operational differences. Level 1 allows standard software running on a general-purpose OS. Jump all the way to level 4, and suddenly you require multi-factor authentication and high-assurance hardware microkernels that can actively detect voltage spikes or temperature extremes and immediately wipe all cryptographic keys. It's a whole different ballgame. Which brings us to Section 3, dangerous engineering assumptions. Let's bridge the gap to technical reality. Misunderstanding these operational environments leads to some really dangerous assumptions in the field. First up is the terminology trap. Having an algorithm with a basic CAVP certificate or claiming your software is quote-unquote FIPS capable does absolutely nothing to satisfy federal mandates. Capable literally just means a module is installed somewhere on the system. The application itself might be silently bypassing it entirely. To be compliant, you must use a formally CMVP FIPS-validated module, and it has to be tested in its specific operational environment. Now here is a massive shift that trips up even seasoned engineers. Developers have historically assumed that standard Linux operating system entropy interfaces, things like dev/random, were sufficient to passively seed their deterministic random bit generators. They basically assumed the host OS would handle all the noise generation. So, was that assumption correct? The answer is absolutely not. Under the current FIPS 140-3 implementation guidance, that old passive loophole is firmly closed. To meet the new SP 800-90B entropy requirements, you now fall under what's called Revised Case 1B. This means your software module must have full entropy source validation, or ESV. It needs direct, raw access to the get entropy interface on the local physical device itself. Standard OS utilities just can't provide testers with direct access to unconditioned noise data. This restriction even limits the use of virtualized cloud entropy pools. And keep in mind, this rigorous standard goes into full effect for new submissions by January 1, 2026. Then there's the virtualization assumption. Simply setting the FIPS equals 1 kernel parameter on your Red Hat host does not magically cascade compliance down to your user space containers or service meshes running inside it. It's like building a fortress of a foundation but totally forgetting to lock the individual apartment doors. Every single container, every proxy sidecar, operates as its own independent logical boundary. All right, on to Section 4, common engineering pitfalls. This is where deployments actually fail in the real world. Let's look at the specific
painful roadblocks where deployments crash and burn in the lab. I mean, imagine failing a $1 million audit just because an automated package update broke your OpenSSL dynamic provider MAC. Painful, right? Or maybe you're aiming for level 2 compliance, but a single Python script gets flagged because level 2 strictly forbids uncompiled source code. We're seeing build failures in older Go environments relying on boring crypto instead of the newer native Go modules. We see MD5 file checks breaking entirely when FIPS mode disables MD5. And under 143-3, if your software lacks a dedicated programmatic show version service that outputs exact module metadata, yeah, you fail. Let's turn this around in Section 5, the Implementation Roadmap, a structured enterprise strategy.
With those pitfalls crystal clear, let's transition from the chaos of failed compliance to a really structured roadmap. The first 4 phases, they are entirely about visibility. You absolutely have to know what cryptography you're running across all your servers and cloud services. You assess the gaps, throwing out non-compliant algorithms like SHA-1 or 3DES. Then, you define an approved, modernized target architecture standardized strictly on NSP 800-140, and you verify that your vendors actually hold active CMVP certificates.
Then, you pilot the changes. Now, Phase 6 usually consumes the most time and effort. Remediating legacy dependencies like stripping out hard-coded SHA-1 or unsupported TLS versions, that requires meticulous engineering. You either upgrade, recompile against validated libraries, or just completely replace the application. And you're doing all of this while collecting rigorous evidence, like startup self-test logs and traceability matrices. Finally, you build sustainment. By implementing robust standard operating procedures like strict key rotation and patch management, and finalizing your evidence repository, you're creating the exact documentation trail that those independent validation laboratories expect well before you even initiate formal coordination in Phase 10. Now, I need you to burn this specific date into your brain, September 22nd, 2026. This is the exact day when all active FIPS 140-2 validation certificates automatically transition to the historical list. That means federal agencies will be heavily restricted from procuring them for any new system acquisitions. The clock is truly ticking for vendors to make the move to FIPS 140-3.
Finally, Section 6, Preparing for Post-Quantum. Cryptographic Agility.
So why the massive urgency to modernize right now? Well, traditional validations can literally take years. Standardizing on 143 today gives you the structural agility to handle what's coming next, the post-quantum transition. FIPS 143 is currently the only validation framework that supports the mandated transition to post-quantum cryptography under the Commercial National Security Algorithm Suite. Standardized algorithms like ML-Chem for key encapsulation and MLDSA for lattice-based signatures are already being integrated into the standard, and they carry strict new rules like pre-operational pairwise consistency tests before they can even be fired up.
Which brings us to the ultimate question for your own deployments. As these standards evolve, is your architecture cryptographically agile enough to survive the transition? If you design your application interfaces today to dynamically swap standard algorithms with post-quantum alternatives without invalidating your core logical boundaries, you'll stay ahead of the curve. But if you hard-code your crypto today, your next audit is going to completely break your architecture. Thank you so much for joining this explainer. Keep learning, keep engineering securely, and I'll catch you in the next one.